Okay, good. Right, so in this first lecture, we will talk about electric charge, what it is, what are its properties, and what can electric charges do. From then, we will move into how electricity is generated. So to understand how electricity is generated, we have to go back to the fundamental thing that makes up all matter or everything on Earth. Okay, everything on Earth consists of an atom. Okay, and inside an atom, you have protons. Protons, we know, are positively charged. Okay, protons, they're positively charged. In the atom, we also have electrons. Electrons, we know as negatively charged particles. And then inside the electron, you have the, inside the atom, you have the nucleus. At the core of the atom, you have the nucleus, which has neutrons. And neutrons, they don't carry charge. We call them as neutral because they are neither positively or negatively charged. So it is the electrons, negative charged particles, and the protons, which are the positively charged particles, which we refer to as electric charge. Okay. So when we say electric charge, we are talking either of electrons, negative charges, or protons, positive charges. Okay, we will use the symbol Q to designate charge, small q or capital Q. They both refer to charge, and the SI unit is Coulomb. And regardless of whether it's a positive charge or a negative charge, these charges follow these three properties: dichotomy, conservation, and quantization. And we will discuss each of these properties. When we say charges have the dichotomy property, we mean that they are either positively charged or negatively charged. Di means two. Dichotomy comes from makeup or anatomy or something like that. So dichotomy meaning the electric charge is either positively charged or negatively charged. And we have this property where if two charges which has the same sign are close to each other, then they tend to repel each other. Hence, we say like charges repel each other. In this figure here, you have two positive charges, and these arrows represent the repulsive force. Yeah. So two positive charges repel each other. Likewise, two negative charges repel each other as well. Notice the direction of the arrows. They tend to push away from each other. Whereas if the charges are opposite, for example, you have a positive charge and a negative charge, then these two charges attract each other. So we say that opposite charges attract each other, whereas like charges repel. Okay, pretty straightforward, right? Okay, dichotomy property. The second property is the conservation property, and this is not new. We're familiar with the conservation of energy, which says that energy is neither created nor destroyed, it's just transformed, such that, for example, mechanical energy is transformed to thermal energy or heat, or kinetic energy is transformed to potential energy. Likewise, charge is conserved, meaning the total number of charges in a closed system is constant. We cannot create or destroy charges, but rather the key word here is that charges are simply transferred from one object to another. Right, so if we relate that to the dichotomy property, right, charges are either positive charge or negative charge. and these charges are in atoms, the atoms make a material. So say this material is made up of atoms. If you have more electrons in these atoms, then we say that this material, if you have more electrons in the atoms making up this material, then we say that this material is negatively charged. But the negative charge in this material was not created. It was just transferred from some other object. Okay? And that's consistent with the conservation property, where you cannot create nor destroy charges. And we will look at how charges are transferred in more detail next, after we discuss these three properties of the charge. And the third property is that charges are quantized. And we have this quantization property. The easiest analogy I can think of to understand quantization property is to think about money. So if you think about New Zealand currency, New Zealand money, the New Zealand dollar, what's the smallest New Zealand dollar that you can have? 10 cents. I think at the moment it's still 10 cents, right? 10 cents is the smallest New Zealand dollar that you can have. And any amount of New Zealand dollar is a multiple of 10 cents. Okay? So we therefore say that New Zealand dollar is quantized because any New Zealand dollar amount is a multiple of 10 cents, which is the smallest New Zealand dollar that you have. $1 can consist of 10 pieces of 10 cents. Right? Except if you go to an ATM machine, ATM, and you want to take out money for some reason, the money you take out is quantized at $20. Right? The smallest amount you can take out from an ATM is $20. Right, so charge in a similar way is quantized. Every observable amount of charge is an integer multiple of what we call the elementary charge. So in New Zealand money, the elementary money is 10 cents. Okay? For the charge, the elementary charge is the smallest possible value of charge, and it is this number here. 1.6 times 10 to the negative 19 coulombs. And every charge that a material can have is an integer multiple of 1.6 times 10 to the negative 19 coulombs. Of course, if we're talking about a proton, then the charge will be positive, and so the elementary charge will be positive. If we're talking about an electron, then the charge will be negative, and the elementary charge will therefore be negative. 1.6 times 10 to the negative 19 coulombs. So if we put the quantization property in an equation, then we have Q equals NE, where Q is the amount of charge, E is the elementary charge, and N is an integer. So any amount of charge Q is an integer multiple of the elementary charge E. Okay. So say, for example, you have a charge Q of, don't know why it's not working. So say you have a charge Q equals 32, negative 32 coulombs. Okay. So it's a negative charge. Then you can determine the number of electrons. We know there are electrons there because it's a negative charge. Then you can determine the number of electrons to be the amount of charge, negative 32 coulombs divided by the elementary charge. Negative 1.6 times 10 to the negative 19 coulombs. Okay. Right, so in a negative 32 coulomb of charge, you have 20 times 10 to the 19 electrons making up that charge. Are we okay with the quantization property? Hopefully makes sense. Okay, any questions about the three properties of the electric charge? Dichotomy, conservation, and quantization. So I think still relatively straightforward. Yeah.
The elementary charge, is it the same for all protons and electrons and all different elements?
Yes. Okay. Yes. So it is, yeah, regardless of any element, because any element will contain the proton and electron. Proton, electron is always the same. Good. All right, so we've learned that inside an atom you have charges, protons and electrons. Most of the time materials are neutral. When you say neutral, it contains the same number of protons and electrons, so that the overall net charge is neither positive or negative. And that's the reason why, you know, objects don't usually attract each other, or if I put this balloon, it does nothing. Okay, the balloon is neither attracted or repelled by me because the balloon is neutral. I'm neutral. Okay, balloon has the same number of protons as electrons. I have the same number of protons as electrons. And right, dichotomy property is that electrons attract protons. And therefore, if the balloon has more electrons and I have more protons, then we should attract each other. But we don't. Nothing exciting is happening. And that's because most of the time materials are neutral. Okay, but we can introduce an imbalance between the number of protons and electrons in a material. And when there is an imbalance in the number of protons and electrons, so that one becomes positively charged or the other becomes negatively charged, then we say that the object is charged, and that's when we generate static electricity. Right, so electricity therefore comes from charges. Okay. Right, and so if we want to generate electricity, therefore we need to charge up a material. Okay? So when we say charging, we only mean that we are introducing an imbalance in the number of protons and electrons, such that the material becomes either positively charged or negatively charged. Okay. So we will learn different ways for charging a material. Okay, just remember the conservation property of charges, right? That they're not created or destroyed, but they're only transferred from one object to another. But if we look at the structure of the atom, in the nucleus you have the neutrons, and the protons are tightly bound in the nucleus, meaning the protons are not free to move about, whereas the electrons, they're free to move around. They're loosely bound to the nucleus of the atom. And so in a material, the electrons are free to transfer from one material to another. So when we introduce an imbalance such that a material becomes charged, when we say that the object is positively charged, we mean that that object lost electrons, so that overall it has more protons. And when we say that the object is negatively charged, we mean that that object gained electrons, so that that object has more electrons compared to protons. Okay. Right. So just keep in mind that electrons are the ones transferring from one material to another, and not the protons. Right. So we will learn these three ways of charging a material, because when you charge up a material, that's when you have static electricity. Charging by rubbing or friction is pretty straightforward from the name itself. Charging by rubbing, That means you start with two neutral objects like the balloon and myself. For example, we have the same number. The balloon has the same number of protons and electrons. It's neutral. But if you charge it by rubbing, you essentially literally rub two materials together. Okay, so you start with two neutral objects and take one object, rub it against the other, and you'll now notice something happening, right? I hope, yeah. I had to make sure I didn't use conditioner this morning because it really works with very dry hair. Because then electrons, what's happening, remember, electrons are the ones that are free to transfer. So what's happening is that electrons from my hair transfer to the balloon. Because I lost electrons, I now become positively charged. Okay, so you have here one object becoming positively charged after the rubbing process. And because electrons move from my hair to the balloon has more electrons now, right, compared to before the rubbing process. And so now the balloon is negatively charged. Dichotomy property says that a positively charged hair will attract a negatively charged balloon. Right? And that's why my hair stands on end. Make sense? Right? Okay, it's also the same phenomenon that occurs when, we don't observe this a lot in New Zealand because our winters are wet. But if you go to some country with a dry winter and you walk across the rug, so you have your feet scuffing across the rug, electrons from the rug transfer to your body. And guess what will happen if you touch a metal such as the doorknob? Have you ever experienced that? Okay. That zapping sensation when you've accumulated a lot of excess electrons and then you touch the doorknob. That electricity you feel is the electrons flowing out of your body, going to the doorknob. Okay, right? Right, so charging by rubbing, you have two objects initially starting to be neutral. You rub both objects together, and as a consequence, one becomes positively charged, one becomes negatively charged. Okay, any questions? Yeah.
If the doorknob is supposed to be neutral, why would the electrons?
Because there are protons in the doorknob that attracts the electrons. Yeah. So in the end, the doorknob then becomes negatively charged, but then it's also grounded, and so you have still a large source of electrons. Okay, I have a question. Yeah.
So if you've got like two objects, so like object A and B, and you rub them together, and one becomes positive, one becomes negatively charged. What's the factor that makes this one charged and that one negative, and not that one negative, and that one positive?
Oh, very good. That was my question. So yeah, and good that you asked, because otherwise I will ask the whole class, right? How do I know that if I rub the balloon against my hair, electrons from my hair transfer to the balloon and not the other way around? What determines that? What's the factor? It's a property that materials have called electronegativity. Okay, and then we won't cover this in class, but it's just out of curiosity. Some materials are more electronegative than others. When we say electronegative, they are electron loving. So some materials naturally attract electrons to themselves. Why? It has to do with the periodic table and the structure of the atom. And so we will not go into much detail there, but just know that some materials are electron loving, and depending on the atomic composition of the materials, we can arrange materials in order of their electronegativity. So here is just an example. going from low electronegativity to high electronegativity. Okay. So for example, if you rub silk with glass, okay, glass is less electronegative compared to silk. Which material will gain electrons? It will be the material that is more electron loving. That's more electronegative, more electron loving. So the glass will gain, the silk is, so we're going from, low electronegativity to high electronegativity. That means silk is more electronegative than glass. Okay. When we say it's more electronegative, it's electron loving. So it will attract electrons. So the silk will attract electrons. The silk will therefore have more electrons. Therefore, it will become negatively charged. The glass will lose electrons, gain electrons, and the glass will lose electrons. So the glass will end up positively charged. The silk will end up negatively charged. Likewise, the balloon, we can consider that as hard rubber. My hair, yeah, which is close to cat's fur. And that's why I know that electrons will go to the balloon, because the balloon is more electron loving. Okay. Rubber is more electron loving compared to my hair. Good.
What if you took two?
Like equal.
Yeah, like if you rub two rabbits together.
I guess they will remain neutral, right? you can try to rub two people, rub two people together, and you probably don't feel that static between two people. But that's a good question. Right. The second way of charging is charging by conduction. The easier way to look at that is charging by contact. Essentially, you have two objects coming in direct contact with each other. When we say in contact, meaning they have to touch each other in order to share charge. Again, remember that electrons are the ones that can transfer from one object to another. So let's look at the example here. You have a neutral object. When we say neutral, it still contains charges, right? It's just that it has equal numbers of protons and neutrons, whereas you have here a positively charged object here. Okay, so we start with a positively charged object and a neutral object. When they touch each other, the electrons are now free to transfer from one object to another. Okay. Right, this figure is what's this? What's the word I'm searching for? So this figure can be misleading in the fact that you might think that the protons from the positive charge move to the neutral charge, because then you can see they're both positively charged. But remember, electrons are the ones that can move. Protons, they're constrained within the nucleus. So what actually happened is that the electrons from the neutral object transferred to the positively charged object. The electrons transferring from the neutral object to the positively charged object neutralized some of the protons in the positively charged object, and therefore you still have a positive charge there. But because the neutral object lost electrons, it ended up to be positively charged. It had more protons in the end compared to electrons. Okay. Right, does that make sense? Okay, because if you start with a positively charged object and a neutral object, this figure can be misleading. But just remember that electrons are the ones being transferred, right? So electrons transfer from the neutral object to the positively charged object, neutralizing some of the positive charges. If you start with a negatively charged object, then it's pretty straightforward, because then the electrons from the negatively charged object can transfer to the neutral object, and in the end, you end up with two negatively charged objects. Right? Okay, the third way of charging is charging by induction. I'd like to use charging by polarization because it's more straightforward to understand it by polarization. But you start with, just like charging by conduction, you start with a neutral object and a charged object. In this example, you have a positively charged rod and a neutral object. The key difference between charging by polarization and charging by contact is that charging by induction or polarization does not make the two objects touch. Okay. So you just bring the charged object close to the neutral object, but not touching. Once the positively charged object touches the neutral object, that becomes charging by contact. Okay. But in this case, they should not touch. But then you have dichotomy property. The positive charges in the rod will attract the negative charges and repel the positive charges. So you have this separation of positive and negative charges in the neutral object. Okay. And that's why it's charging by polarization. The charges are polarized, so that if I cut the objects in two, then I sort of have two objects with different charges, and I end up with two objects, one positively charged and the other negatively charged. And I have a good example here of charging by. Right. So any question about charging by induction?
Is that how the wireless phone chargers work?
Wireless phone chargers, they work by electromagnetic induction. And we will look into that 2 weeks from now. I have exactly a video with, yeah. Right, so two objects, can and a balloon, they're both neutral, right? Object materials, in the beginning, they're neutral, nothing's happening between them. Okay, I start to introduce charge in the balloon by charging by rubbing or friction. Electrons from my hair transfer to the balloon. The balloon now becomes negatively charged. Right, have to make sure I put enough charge in there for this to work. Right, and then that will happen. This is how you can train a can, right? Make it do what you want to do, right? And so what's happening there? What happened there? So balloon acquired negative charge from my hair. The balloon is negatively charged. The can was just sitting there, right? So the can was still neutral, right? If I bring the balloon close to the can, but it's not touching, right? They're not touching. What's happening? What's happening to the charges in the can? Yeah. So the can is neutral, meaning it still has positive and negative charges. So the balloon is negatively charged, meaning the positive charges in the can move to one side because they're attracted to the electrons of the balloon. The electrons in the can move to the opposite side because they are repelled by the electrons in the balloon. And so if I were to cut the can in half, then I end up with half of the can being positively charged and half of the can being negatively charged. Then I would have induced charge in the can by charging by induction. Right, and you will do this in the first lab. You will investigate these different modes of charging. So the fact that, yeah, so I did that demo, so you don't need to watch the video. So here's a question, which is a revision from semester 1. The can was initially at rest, right? And then the balloon caused it to move, meaning the can accelerated from rest. So according to Newton's laws of motion, what was present in order to make the can accelerate? Yeah. Force, the keyword, right? It's what makes an object accelerate. It's force, right? So there was force between the balloon and the can, and that made the can move, right? So the fact that the balloon made the can move is an evidence that there is force existing between charges. And as we've seen, dichotomy property said you have this repulsive force if you have like charges, and you have this attractive force if you have opposite charges. And it was Charles Coulomb who found the relationship between the force, relationship of the force between two charges, and we call that Coulomb's law. So Coulomb's law is given by this equation. F is the force, Q1 and Q2 are the charges of the charges that attract each other. R, that's the distance between the two charges. K is a constant, 9 times 10 to the 9 Newton meter squared per Coulomb squared. All right, so we've learned that force is a vector, right? So force should have direction, and so direction is important as well. But in this Coulomb's law, I use these 2 bars. So the 2 bars around Q means absolute value, meaning ignore the signs of the charge, whether it's positive or negative, simply ignore the sign. And so this equation for Coulomb's law gives you the magnitude of the force. This is how you calculate how much force one charge exerts on another charge, right? Disregard the signs of the charge. If you were to find the direction of the force, because force is a vector quantity, then just use the dichotomy property of the force. So the force always acts along the line joining the objects. So if you have these 2 positive charges, simply draw a straight line connecting the 2 charges and use dichotomy property to determine the direction of the force. Because these are 2 positive charges, then the forces repel each other, and hence you get the direction of the force. So just a note here, because often students are confused by this subscript. So the subscript here tells you which charge you're talking about. So F12 means the force on charge 1 due to charge 2. So this is just a subscript indicating which charge exerts what force. Okay, so the notation we will use is F12 means it's the force on charge 1 exerted by charge 2. Right? So calculate the magnitude of the force using Coulomb's law, remembering the 3rd law of motion, that the force exerted by charge 1 on charge 2 is equal in magnitude but opposite in direction to the force exerted by charge 2 on charge 1. Right, so a little bit of an exercise before we move on to calculating the force. Okay, I have 4 charges here, Q1, Q2, Q3, and Q4. Find the, it says here, draw the vectors, the force vectors exerted on charge Q2. So we want to find the direction of the force exerted on charge Q2 by all the other charges, Q1, Q3, and Q4. So how do we find the direction? I think I'll. Oops. Right, so force is between two charges, right? Force in Coulomb's law, in the force equation, the force exists only between two charges, Q1 and Q2. So if you have more than two charges, the way to approach this is to look at two charges at a time. You want the force on charge Q2. So first consider the effect of charge Q1 on charge Q2. Draw a straight line connecting the two charges and use dichotomy property to determine the direction of the force. Right, do the same thing for charge Q3, imagining as if charge Q1 and Q4 does not exist, and you're only looking at charge Q2 and Q3. Draw a straight line connecting those two charges and use dichotomy property to determine the direction of the force. And do the same for every charge present around Q2. Okay. So therefore, this is your free body diagram, right? Free body diagram, which shows all the forces acting on charge Q2 because of charge Q1, Q3, and Q4. So of course, if you still need to get the net force, then yeah, we've learned techniques of how to get the resultant force of force vectors. Right, so this is how you determine the direction. Now for the magnitude, let's look at this example. You have these two charges, Q1 and Q2. Q1 is negative, Q2 is positive. The amount of charges are here. Okay. Take note that's microcoulombs times 10 to the minus 6 times 10 to the minus 6. And they are separated 0.3 meters apart. Okay. And we want to calculate the electrostatic force on Q2 due to Q1. All right, so the way to do this is to use Coulomb's law, KQ1, Q2 over R squared, to find the magnitudes. K is just a constant number. Q1 is the charge. Again, remember there's a times 10 to the minus 6 because the charge is given in microcoulombs. Okay. Right, the important thing here is notice Q1 is negative, but in my calculation, I disregarded the negative sign for Q1 and I used only positive 8 times 10 to the minus 6. Right, D, that's the separation distance, and don't forget there's a square there, so don't forget to square the distance. This will give you the force in newtons. This is just the magnitude or the size. Right. And once you've determined the magnitude or the size, you then determine the direction using dichotomy property. Since you have a negative charge Q1 and positively charged Q2, then those two charges should attract each other. Okay. And the direction of your arrows, the arrows, force arrows that you've drawn, will give you the direction of the force on Q2 due to Q1. So we're looking at the force experienced by Q2. It's this force that we are after, right? And if you look there, the force is directed to the left, and therefore the direction is negative I hat, or to the left. Okay, so I hat, just recall our the convention. Positive x direction is positive I hat, positive y direction is positive j hat, Positive k direction is k hat. Right, so the direction here is negative I hat. Cool. Right, and if you wanted to find the force on Q1, force on Q1 due to Q2, then if you calculate the magnitude, you'll see that you'll end up with the same magnitude because you're still using the same Q1 and Q2 values. But what's different is the direction. If you, as you can see in the force free body diagram here, the direction of F1 is opposite the direction of F21. Direction of F12 is the opposite the direction of F21, but the magnitude is still the same, 2.4 newtons. Right. Okay, and finally, before we wrap up this lecture, if you have more than 2 charges, okay, so for example, here you have 3 charges and you want to find the force on Q2, how do you find the force if you have more than 2 charges? The trick there is to use superposition, meaning calculate the force between 2 charges, because Coulomb's law only involves 2 charges. So look at 2 charges at a time, find the force on Q2 due to Q1, ignoring the presence of Q3. Okay, so you do the Coulomb's law to find the magnitude, and then do your free body diagram to find the direction involving these 2 charges, Q1 and Q2. And then do the same thing. Find the force on Q2 due to Q3, ignoring Q1. So calculate the magnitudes of force due to Q3 using Coulomb's law, and then draw your free body diagram to find the direction. And then finally, get the net force by adding the 2 forces that you've calculated from each. Right. So yeah, the real key concept there is that if you have more than 2 charges, then look at 2 charges at a time, because force between charges exists, force exists only between 2 charges at a time. But overall, you can add up each of the individual forces to get the net force on a charge. All right, there's an example here, but we've run out of time. So we'll look at this example in the beginning of the next lecture. But this is on stream, so feel free to try out this example if you want to have some practice. But otherwise, have a good day, everyone, and I'll see you tomorrow in lecture 2.